Okay, good afternoon once again. So today, this afternoon, we're going to finish off the chapter on Laplace transforms. This is chapter 2. We're going to look at a nice example of an ODE. Look at a solution and various different cases of the solution. And then also I'm going to leave you with some extra exercises as well to do with various properties of the Laplace transform. Okay, so, but first of all, before we get on to the example, I want to just very briefly just look at this final section, section 2.6. Section 2.7 there on the limit relationships and the final states. So all this, it's really just a piece of terminology here in section 2.6. Sometimes we can see a solution to a differential equation is made up of a number of different terms added together, some linear combination of terms. And this terminology of steady state and transient is sometimes used to describe properties of those various terms. And they're quite suggestive names. A steady state term is a term whose influence is always around. It doesn't diminish with time. Whereas a transient term, as the word suggests, is a bit of the solution, a term of the solution, a component of the solution whose effect diminishes over time and disappears over time. So for instance, in this particular second order ODE here in 2.54, the solution that comes out is this function y of t here in 2.55. So you can see here it's a linear combination of three terms. There's a cosine term, an exponential term, and then that constant term 2 at the end. So the first and third terms there, the cosine bit and the constant 2 bit at the end, we could describe those as being steady state terms, because their influence is always around. If you look at them at any time t, you'll always find those two terms influencing the solution to more or less the same degree. Now the cosine bit is periodic, and its effect does kind of wax and wane as time goes on. It cycles through values between -1 and +1. So sometimes it's having a small effect, it's close to 0. But as you let time run on, the term persists. Whereas the exponential term in the middle, because it's 2 times e to the minus t, as time goes on, the effect of that is going to become less and less, because it's e to the minus t, so as t increases, it's going to converge to 0. So that middle term, the exponential term, we could call transient. So it's just a bit of terminology. Sometimes people will talk of the steady state part of the solution and the transient part of it. Okay. So, to finish off the chapter then, we're going to look at an example. There's an interesting ODE example. And we'll be able to obtain its solution via Laplace transforms. But we'll skip the nitty-gritty details and we'll just pick out some interesting aspects of the solution. So there's a bit of a diagram to go along with it. Explain these various things as we go on. So you might go, might not look like it, but this is a rudimentary model, meaning quite a simple model, not that many aspects to it, but a rudimentary model, let's say, of a spaceship landing gear. So this is going to be something that's going to be dropped onto a planet or onto a moon or something. So what do the various bits of this diagram represent, and how do we kind of quantify them? Well, so this thing here is a spring. This thing here, and this thing here is what's called a damping pot. And this is what we think of as our spaceship up here. Okay. So what we've got in this diagram here is a spring with a resting length Okay, so the resting length of the spring is, if you just put the spring on the table, it's just the length that naturally goes to, okay, where the ends of the spring are free. And it goes to that. And then if x is the displacement of the resting length, then the spring exerts a force F, given by F is equal to minus K times X. K is just some coefficient attached to the spring. It's a measure of the strength of the spring, if you like. So springs, when you squash them, they exert a force they want to lengthen again. And when you stretch them off their resting length, they exert an opposing force. The spring wants to shrink back again. And the amount of force that they exert is proportional to the amount that you've either shrunk or expanded them away from the resting length. Okay, it's the spring coefficient. A damping pot is slightly different. A damping pot also resists stretching and compression. So springs do that as well. Springs resist compression and resist stretching. They don't like to be stretched and compressed. They fight against it. And so do damping pots, but damping pots don't do it according to the amount by which you try and compress or stretch them, but how fast you try and do so. Okay? So they resist with a force F given by, and it's minus B times x dot or x dash. So this is x dot is dx. So the damping pot, if you try and stretch it really fast, it fights against it with a large force. If you try and stretch it really slowly, it won't put up that much of a fight. The force that it resists this with is proportional to the velocity with which you try and stretch it. And similarly, if you try and compress it, try and push it the other way, it resists that also. And the reason they're both there in the landing gear, well, if you're going to drop this thing onto the ground, obviously you don't just want to drop your spaceship onto the ground and it just crashes into the ground. So putting the spring there is some element of suspension. So you drop it to the ground, it's got a spring on it. But you don't want to drop it from a big height onto the ground with a spring and then just watch it bounce up again and so, really, really high, then come down again and bounce. And you don't want it to do too much bouncing. So the damping pot there is put there to try and dampen down the effects of the spring. The spring is still there to cushion the impact, absorb a lot of the force of the impact. The damping pot is put there to stop the thing going mad under the influence of the spring, just bouncing all over the place. So suppose, so this spaceship is mass m, so the m is there for the mass of the spaceship. So suppose that the mass is 50, and we'll take for these the coefficients of the damping pot and the spring to be given by these quantities here. Very precise, 474.5. Don't worry about it too much, the precise values. When dropped from a height h, so this thing is just going to be dropped from a certain height, it impacts the ground so at the time at which the wheel is going to be touching the ground, the velocity of the thing will be the square root of 2 times g times h, where g is the acceleration due to gravity. And the question here is just to, or the direction here is to investigate the effects of different drop heights. Different drop heights and maybe different damping coefficients. Okay, you can imagine that damping coefficient B, which is the strength of the damping pot in a way, that might be, we might be able to finely tune that by adjusting the parameters of the damping pot. And so just if we can try and set up an ODE for this, get a solution which measures the position of the spacecraft, and then maybe we can see what effect changing some of these parameters have. So the way we're going to do it is, here's the thing hitting the ground. So here is it at the point, so this is t equals 0, the time of impact. And we're going to measure the position of this thing with an x-axis. It's going to run here. This is going to be position 0. This is just, say, the midpoint of the spaceship. So that's our x-axis. So we're going to be interested in the vertical position of this thing. It's been dropping towards the ground, and there we're picturing it at time 0, the moment it impacts on the ground. And we're going to track its position after that. And we just have to decide on the positive direction of the x-axis. So we're going to have the x-axis going up this way. So upwards is the positive direction of the x-axis. And this is position 0. This is the position of, say, just some mark on the spaceship, time 0, the exact point of impact. So using Newton's third law, which is force is mass by acceleration, which is mass by x double dot. Second derivative of position, acceleration is. We can get an ODE for this. So the ODE will look like mx double dash. This is m times the second derivative of the position. And this should be equal to, so you add up the other forces at play. So the other forces at play are the gravitational attraction on the mass, the effect of the spring, which is minus k times x, and the effect of the damping pot, which is minus b times the first derivative. This is the spring effect and the damping effect. And we've got initial conditions that at time 0, x of 0 is 0, which means the tracking the position of the spacecraft, it's at position 0 at impact time, time 0. And the initial velocity is square root of 2gh. Just a little bit worried about my positive direction. Now, figure things out, I might go back and reverse the positive direction of the x-axis. We'll leave that alone for now. So there's the second order ODE, initial conditions. So that looks perfectly amenable to the Laplace transform method. Okay? So this is readily solved with Laplace transforms. You can simply transform the whole equation. You get the mass of the spacecraft times s squared times the Laplace transform of x minus s of x naught minus the initial value x dot. You transform the constant ng, just goes to ng over s. Transform minus k times x, it goes to minus kx bar. And then you've got the transform of the first derivative of x, so it's going to be sx bar minus x of 0. And then putting in initial values, solving for x bar gives this. So we've got the mass times g. We'll have s over, we get this quadratic coming out, ms squared plus bs plus k. This is the coefficient of x bar on the left everywhere, so we're dividing out by it. Then you've got plus m times the square root of 2gh over ms squared plus bs plus k again. So it's readily solved with the Laplace transform method, except we haven't fully solved because we have to then take the inverse transform. But rather than messing around for ages with the table on that, we might get the computer to do a bit of work for us in this, and I'm going to want to visualize some of the solution curves. So here, and I'll make this worksheet public and put it up on the Moodle page to be able to get this afterwards and experiment around with it yourself. So I've got this worksheet here to illustrate the solutions. Up here, I've just got the definitions of the constants. So we've got our spaceship of mass 50 kilograms, say. Coefficient of damping 180, the spring coefficient 474.5, and the gravitational acceleration 9.8. So execute those, define those values. That command var sth just sets up symbolic variables, st and h, similar to the MATLAB sims command. Then because this quadratic term in the bottom, ms squared plus bs plus k, because that comes up a few times, just define that as quad. So it's 50s squared plus 180s plus 474.5. Those are the values of m, b, and k. And then you can see in our solution for x bar, there's two terms. There's the first term and the second term. So the first term is mg in the numerator. The second term is m square root of 2gh in the numerator. So I just set these up as x term 1 and x term 2. X term 1 is just got, the reason I keep them separate is x term 1 doesn't have any dependence on h. Its only dependence is on the coefficients m, b, and k. So you can see here I've defined x term 1 to be that first term, but then I take its inverse Laplace transform. So the command in Sage for doing that is inverse underscore Laplace. You have to name the two variables that we're using, s and t. This is the solution it gives to you. There's a constant bit. And then this exponential bit times all of this. So you could definitely see this is exponential to a negative multiple of t. So this whole first term is going to be transient. Its effect is going to disappear over time. The steady state bit contribution from here is going to be this quantity here, which is very close to 1, you can see. Then the second one, x term 2, well, I set that up as a function of h. It's m times the square root of 2gh divided by the quadratic. And I take its inverse Laplace transform again. Just going to show that so you can see. It types that nicely. Okay, so it's some kind of fraction, approximately 2 times square root of h times that exponential, that's a transient exponential, e to the negative multiple of t, multiplied by a sine of 5 over 2t. Okay, so that's the effect of h. So those are the two, you will have to add those two together to get the total solution. Remember, the inverse transform is linear. So we take the inverse transform of that whole thing and just add together the individual inverse transforms. Every bit of the solution that we're looking at there is transient, except for that 980 over 949 there. So that 980 over 949, which is approximately 1, that's going to be the rest. That's going to be the final resting position of the spacecraft. So I think I did make a slight. I did indeed. I did make a slight mistake here. So the positive direction of the x-axis is not upwards; it's downwards. That's the positive direction. And that makes, sorry, yeah, that's what was causing. Because the fact I've got this contribution is plus mg, that means gravity is acting in the positive direction. So that the positive direction must be downwards. So the positive direction points down. Sorry about that. Okay, so let's actually have a look at these solutions. So x of h, which itself is going to be a function of t. See, there's loads of t's in here. Cosine t, sine t, exponential of t. So it's a function of t as well. So x of h is x term of 1 plus x term 2, which has a dependence on h. And so the question was investigate the various effects of drop height on the thing. So here I've plotted minus x of 10. So this is dropping the thing from 10 meters up. Okay. So dropping it from 10 meters up. So now my positive direction is going down. Slight confusion about what the positive direction is here, but never mind. So, but what you can see here in the shape of the solution curve, so the thing is dropped from 10 meters. We're only seeing the action from t equals 0 onwards. So from the moment that it just first makes any impact with the ground. So this looks like the expected kind of behavior. The position of the spacecraft, continues to fall until it reaches some minimum position of like a height of minus 2.5. So it's an extra 2.5 meters approximately below the position where it first impacted. Okay, but all the time the spring is trying to resist this motion, and so eventually the spring is starting to win out and it manages to push it back up, and there's a little bit of a bounce until it finally settles back down there, and then its position is constant, or its position is more or less constant, just slowly converging to that final resting value. So that would be the height 980 over 949, approximately 1. And this is why I'm plotting. Yeah, so I'm correct in the positive direction is pointing downwards. In the positive direction is pointing downwards, but just because we're imagining the thing falling and then bouncing towards the ground, I've just plotted minus x of 10 just to turn it the right way up that it would appear if you were looking at it. Okay? So the spacecraft is squashing down, bouncing up a bit, and then returning to an approximate constant value. If we weaken, so this coefficient B is the strength of the dampening pot. If we weaken that a bit, maybe so it was 180 initially, if we send it back now to 30, so this is a much weaker damping pot. So if we really execute everything, well, I shouldn't have executed the last graph, but while it's generating there, yeah, so if the damping pot is a lot weaker, that means the spring is going to have much more of an effect. Remember, the damping pot is something that resists motion according to the speed at which you try to move it, stretch it or expand it. So if the damping pot is far weaker, you're going to see the spaceship bounce around a lot more. Okay? So if the damping coefficient was only 30, it would bounce down, it would compress its landing gear down to by 5 meters. Okay, so as it's falling, the landing gear isn't compressed, might even be slightly stretched or whatever, but assuming it's just at its resting length. Then it impacts the ground and it's going to compress the landing apparatus by a further 5 meters. But then the spring is going to push it back up and it's actually going to lift off the ground again. So it's going to stretch up, it's going to reach a height of just over 1 meter and so on, come down. And it's taking a lot longer for its motion to settle down. On the other hand, if we increase the effect massively of the damping, put it to 300, it was 180 to begin with. If we make it 300 now, what kind of effect are we expecting? Now, this is going to dampen down the action of the spring by an awful lot. Okay? We may not even see any, maybe just a very slight oscillation. Well, still some oscillation. But very little of a return bounce. So it hits at time 0, it's at position 0, it compresses the landing gear by 2 meters, But then there's virtually, it doesn't bounce back again. It just slowly, it bounces back up, but it certainly never gets back up anywhere near its initial position. And just very quick convergence then to this -1. So if we put it back to the original damping effect, which was 180, re-execute these. This is the original solution. Then we can start to look at the effects of different heights. So in these commands here, again, so I plotted what the solution. So we're plotting x of t here of the same range, but I'm putting in various different heights. So putting something that isn't really dropped at all, so just placed on the surface and then allowed to settle. That would be x of 0. X of 5 is something that's dropped from a height 5 and so on. X of 10 and so on. All the way up to something that's dropped from a kilometer high. And I just superimpose all these plots and make them all different colors. So you can kind of view them all at once and see the different effects of dropping from various heights. So the blue one, this first one, that's something which isn't dropped at all, really. It's just kind of placed on the surface and just allowed to settle into its landing gear. So begins at a height, begins at position 0 and just slowly compresses, or just, settles down and compresses the landing gear a little bit, and then is just at its final resting position. Then the different colors, red, green, orange, are being dropped from progressively higher heights. The thing then, which is dropped from a kilometer high, is going to want to compress its landing gear by 20 meters. But maybe that's outside of the parameters of what you could feasibly build. A compression, a landing gear which could be compressed up to 20 meters. So maybe if you were going to be dropping from a kilometer high, maybe you would want, this would be a sign that you want to go back and tweak the parameters a bit, make the string a bit stronger, perhaps. If you make the string a bit stronger, it'll resist being compressed so much. So you won't have this huge compression amount of 20 odd meters. So this example just shows to you, how a fairly realistic model or setup, getting the second order ODE out, applying the Laplace transform solution method, and getting a solution out which still retains some dependence on a parameter, here the height h from which you're dropping it, and just using some simple plotting techniques, being able to see the effects of different values of the parameters. So that black one, which compresses down to 20 there, if we were to go back up and boost the spring a bit, if we were to boost the spring, say, up to 600, we would probably see far less compression in this final graph, hopefully. Less compression anyway, just wait till it generates. Hasn't had much of an effect. Maybe it's had a slight effect. Maybe we need to investigate it a bit more to see the effect brought out. Okay, so before I leave you with this chapter, I would just like to, because I believe in the utility of exercises and further questions, just like to leave you with some further properties. Further properties of the Laplace transform, okay, which you might try your hand at proving. we proved certain properties which we needed in order to set up our method for solving the ODEs. And there was nothing too fancy in the proof methods we used. We just always looked at the original definition of the transform in terms of the integral definition. And just by carefully treating the integral, prove the desired results. And these are all quite similar in spirit to that. So the first one is, what if you had to take a Laplace transform of a function, and instead of evaluating the function f at t, you were to rescale the argument? Now we proved something similar like this where we shifted the argument. We evaluated f at t minus a, and we then had it multiplied by a Heaviside step function. But if we perform a different operation on the argument here, we rescale it by this rescaling factor 1 over a, where a is some constant. You should be able to investigate this and prove that it's a times the Laplace transform, so f is the Laplace transform of the original function f of t. Now this u function, or this f evaluated as a rescaled argument, has that slightly different Laplace transform, a times f of as. Secondly, what if we had a nice function f, which we knew what its Laplace transform was, and then this is quite a common operation to perform on a function. It's the continuous version of having a sequence of values and summing up all the values. Here we've got a function f of lambda, say, and we're going to sum up all its values between 0 and t. So this is the continuous summation of all the function values from 0 to t. So you're integrating the function from 0 to t. So the integral, the whole thing, is a function of t. Change t, you make the integral longer, you're accumulating more of the values of the function f. In the Laplace transform side of things, this equates to multiplying the Laplace transform of the original function f of t by a factor of 1 over s. Again, these can be readily proved by looking carefully at the integral definition of the Laplace transform here on the left. Now this is maybe the third or fourth time I've said this, but it's an important warning. I'll probably still see a few people, probably the people who aren't here, maybe make this mistake. But remember, the transform is not multiplicative. It is nice when things are multiplicative. You certainly appreciate it when they are. And when they are, you can draw a lot of conclusions from them. In number theory this morning, we were looking at a particular function which was multiplicative, and that was great news. It allowed us to do a lot of things with it, and will do in the future. But things are not always so nice. So it's not multiplicative, meaning that if you have two functions f and g of s times f of s, if you multiply their transforms, it's not equal to the Laplace transform of f of t times g of t. Maybe in special situations, but they might just be considered flukes or that. But in general, we do not expect the Laplace transform of the product of functions to be the product of the individual transforms. Don't think that it is. However, that doesn't mean that this construction of multiplying together transforms doesn't have any connection to the functions f and g. I mean, it's a very natural thing to do with functions, multiply them together. So the question, is there Does multiplying the transforms correspond to anything? It certainly isn't the transform of the product, but does it correspond to something? Well, in analysis and integration, there is this notion of the convolution of f and g. And convoluting two things means forming a new function h of t, which is the integral from 0 to t, and you're kind of summing, it's basically going to be summing up products of values of f and g. You're kind of multiplying f and g. You are multiplying their values that they take between 0 and t and adding up the results, integrating the results, but you're doing so in opposite directions. So the values of, you're taking the values of g between 0 and t, but multiplying them by the values of f taken in reverse. So g runs through its values starting at 0 going up to little t. F runs through the same set of values but in the reverse direction. It starts at lambda equals, see the integral is lambda 0, lambda equals 0 to lambda equals t. So the function f starts off taking the value f of t. And then as lambda increases from 0 to t, the argument of f there decreases down to 0. So you're taking the functions, the values of g from 0 to t, the values of f from t down to 0, multiplying them together and adding them up. This construction is called a convolution of f and g. And it is this new function, whose Laplace transform is the product of the two Laplace transforms of f and g independent, f and g on their own. Okay, all these can be proved by using various techniques or ideas of integration. And just the plain old definition of the Laplace transform of something, the integral, the exponential, e to the minus st times the function xt, integrating that with xt. Just apply that integral definition to each of these problems here and flex your integration muscles on it. Those are some good workouts in group technique, integration technique, dealing with the Laplace transform. Okay, so that kind of parks that chapter then for the moment, so we come back to it maybe in revision, we do some past exam type questions with it and so on. So the remainder of my lectures will be on the third chapter on Fourier series. So we'll begin that next week, and we should deal with that in a few weeks, and then we still have a few weeks left for revision activities. Okay, so I shall see you next week. Thank you for listening.